Hawking, his great contribution was to start thinking about what is the consequence of quantum mechanics for black holes. Imagine you have some pair of entangled electrons. When one of them falls into the black hole and the other one stays outside. According to quantum mechanics, they're still entangled, but if you're an observer here with this in your hand, there's no way you can know what the other one's doing. Well, it turns out that if you now take this CFT and look at finite temperature, look at some excited state, not the lowest energy state. That's at some temperature here. So this is a temperature T. Then in the string theory, you get a horizon. And its Hawking temperature of this horizon is precisely the temperature of the CFT. It's a very complex entanglement of everything entangled with everything else, like in the SYK model. If you're an observer outside and you're looking at the black hole, to very good accuracy, you may as well assume there's an SYK model sitting there. I'm not saying there actually is, but it captures all the right physics.
This week, Xinghui and Misha spoke with Dr. Subir Sachdev, one of the world's leading theorists of quantum matter. For decades, he's been at the center of efforts to explain high-temperature superconductors, strange metals, and the unexpected connections between quantum materials and black holes. We dig into what makes these systems so mysterious, why they matter, and how new theory is finally closing in on answers. Please welcome Subir Sachdev.
When I was in graduate school, I wasn't sure. I wanted to do theoretical physics, and in those days, this was just the mid 80s, when the Standard Model had just been understood, and there was a lot of excitement in particle physics, a lot of progress going on. But everyone was excited about string theory at that time, but it seemed to me that it was very mathematical, and it would be very hard to test things in experiments. So I wanted to do something that had to do with things you could test in a lab.
In which year was this?
So I joined Harvard as a graduate student in 1982.
Because I went through the exact same trajectory in 2007. I wanted to be a string theorist, and I said, "Oh, this is all math. Let's do something that's testable in the lab." So 27 years later, the same. It's the same trajectory.
Yeah, I mean,
yes.
Okay, the things are slightly different by then, but yes, it's the difficulty of testing ideas in particle physics and string theory, was already clear in the 80s. Certainly in the 70s, there was a lot of incredible progress. But there were also people in the 80s saying, well, condensed matter physics is also kind of a finished field. There was the renormalization group that you mentioned. There was a theory of phase transition, and there was the BCS theory of superconductivity, well established. So it seemed like, everything was all set. But what happened, fortuitously, or were already starting to happen when I was in graduate school, there were some amazing new phenomena discovered in condensed matter physics. So I guess I would say the earliest was the quantum Hall effect, the integer quantum Hall effect. I think that was 1980 when I was still an undergraduate at MIT, where they observed that in a high magnetic field, when you have electrons in certain semiconductors, that they would have a resistance in the direction orthogonal to the magnetic field that was just given by integers times the charge of the electron and Planck's constant. And this was completely amazing because people at that time, previous to that, used to look down on condensed matter as something very messy. You have these complicated crystals, lots of impurities. You can never say what's going on. And amazingly, this complicated, messy system showed something that only depends upon Planck's constant and the charge of the electron. And it was quantized to some very high accuracy. So there were things in the air. So the integer quantum Hall effect had been discovered, and then there was the fractional quantum Hall effect. And a lot of people were very excited about this. Yeah. So I didn't work on that at that time. But when I was in my postdoc, high TC, cuprates, high temperature superconductors that I show in this picture here, they were discovered in 1986 when I was a postdoc. And, so I dropped everything. I was working on other things at that time. I was working on quasi-crystals and other phenomena that had been discovered a bit earlier. and I jumped to working on the cuprates. And in some sense, I still am 40 years later. But I would say, it's sort of like the key cuprate problems, there's been a lot of progress and maybe hasn't been fully solved yet. There's still some issues outstanding, but there's been amazing progress. But what's happened is that sometimes I liken this to Fermat's last theorem. It's not so much solving Fermat's last theorem. Of course, that's a great achievement. It's all the things you discover along the way. So thinking about the cuprates has led to kind of a revolution in physics, new ideas on many-body quantum entanglement, on quantum phase transitions. These have influenced all kinds of other aspects of physics. In fact, quantum error correction, ideas in quantum error correction came out of ideas on spin liquids, which people first started thinking about because of the cuprates. And there are many other examples and then of course, personally involved with the connection to black holes. So these were offshoots of ideas that came from this experimental discovery and the theoretical work that was done on it.
So maybe like touching the base on the cuprates, which
Yes.
seems like was the pivotal point in your story.
Yeah.
At that time, back in the 80s, what was the tackling directions for solving this problem?
There were a lot of proposals right away. Some people said, well, it's just another version of BCS. Somehow the phonons, which lead to pairing in the old superconductors, are also involved here. But nobody could really make it work. I think the suggestion by Phil Anderson in already 1987, I think that was, that it has to do with strongly interacting electrons and possible entangled states of matter. He didn't use the word entangled state or even the word spin liquid because it didn't exist. The ideas didn't exist of what such states look like for a many-body system. He called it a resonating valence bond state. And today we would say that's a new state of matter which has entanglement on a very large scale. So I think anyway, so that was one set of ideas, but there were many related ideas all related to somehow not so much the coupling of the electrons to the lattice, but strong electron-electron interaction leading to completely different states of matter that had not been studied at all before. And there's been a huge revolution in condensed matter physics in understanding these different possible states of matter.
So would you say that cuprates were, in a way, your superhero origin story as a formed scientist, or maybe there's even a superhero origin story before that in your childhood where you felt like, oh, I need to be a scientist? Is there anything you recall that drew you even just to science or physics?
Yeah, well, I always loved science in school. I think went to very good school in Bangalore in India. And my father was an engineer. He was working on telecommunication with satellites. He was involved in that.
Did he want you to be an engineer too?
Well, every Indian father wants his children to be an engineer or a doctor. So
Every Chinese father too.
So I did start out actually as an electrical engineer at MIT, but I switched to physics as I went along. But yeah, so I don't know. I used to read a lot of books. I think Feynman lecture in physics, which I read in high school, were very influential, and I really enjoyed the exciting way he was explaining all these modern discoveries, well, in the early 20th century of quantum mechanics. So it was. It just seemed like, worth a shot. You try it and see if it works for you, and if it doesn't, well, there's lots of other jobs you can do with the training as a physicist.
It makes a lot of sense. I absolutely agree.
maybe if we can just walk through like the story behind the superconductors, like let's say starting from 1910s, 1911 when the
in fact, here it is. So here's I have a picture here.
Okay, that's great.
Camerleonis in 1911, and this was a discovery. This is his refrigerator here, which is as big as a room, and which you can still see in Leiden in the Netherlands. And what he found was that if you cool mercury down to some very low temperature, negative 269 degrees Celsius, its resistance to carrying current just suddenly went to zero.
Was it him? I have heard some stories that it was his PhD student who slept while doing the measurements.
Yeah, I've heard that too. But it was Camerleonis who got the Nobel Prize.
I see. That doesn't matter.
I mean, it was he was building. I'm sure it was his idea to build this refrigerator and cool metals down to very low temperature.
What was this? Was it like a dilution refrigerator, or what was the system he built?
Actually, I don't know. I think they were pumping.
Question for experimenters.
They were pumping on helium, basically. He also had succeeded in liquefying helium, but yeah, dilution refrigerator I think came later because that involves helium.
Maybe yes.
Yeah, that came quite a bit later, I think. Anyway, so it was a complete surprise. And they were really, this was 1911, Schrödinger's equation for the basic equation of quantum mechanics was written down in 1925. So there was no understanding of what
no quantum theory.
There was nothing. I mean, people had no idea how to explain this. So then the history is that after Schrödinger's equation, there was the Sommerfeld. Sommerfeld came up with a theory of electrons in metals. Okay, and just before that, there was also the idea of Pauli, that electrons obey the Pauli exclusion principle, that no two electrons can sit in the same state. So what Sommerfeld showed was that if you assume a metal like copper is made up of, or even mercury at higher temperatures, is made up of electrons that are just moving in plane waves and freely in the wire. And the only thing you need to know about their quantum properties is that they obey the exclusion principle. So, but you can solve Schrödinger's equation for each electron individually. But then when you take the collective properties, you have to just remember that they obey the Pauli exclusion principle. They're fermions, as we say.
They don't like to stick together.
Right. And so from this fermion property, Sommerfeld showed you could really understand many things about metals. In particular, the specific heat of metals, has a certain temperature dependence, and you could actually understand that extremely well, quantitatively. And so really it was the Sommerfeld paper which was the start of what we call solid-state physics. That's when we started to understand why metals are metals and why insulators are insulators. That came a bit later with Bloch understanding the effect of the periodic potential of the atoms in a lattice, and then semiconductors. So this was an absolutely central discovery, which eventually was crucial to making transistors and integrated circuits and lasers and everything else. It's the basis of our technological revolution. But superconductivity took a while, and it wasn't understood until 1957 by Bardeen, Cooper, and Schrieffer in what we call the BCS theory. But the basic idea that the key new ingredient you needed actually had already appeared in 1925-26. All of these, 25-26 was an amazing year, where 100 years ago today, where all these new ideas came about. And that was the idea of Bose-Einstein condensation. That if you take, so I mentioned fermions earlier, which are particles that obey the exclusion principle. And bosons are particles where you can put any number of particles in the same quantum state. So light, the photon, the basic ingredient of light, is a boson, and that was understood by Bose, who was an Indian scientist, also an inspiration to me. And then what Einstein said, well, suppose you had not light, but some particle which had a mass, like today we'll say a helium atom, for example, that behaves like a boson. Then under a certain temperature, the helium atoms, these bosons are moving around and with all kinds of velocities. But below a certain temperature, a large fraction of them, a finite fraction, would all go into zero velocity state, the zero momentum state. So this is the phenomenon of Bose-Einstein condensation, which Einstein showed in 1926 will happen very naturally by a calculation which is the mirror image of Sommerfeld's calculation for fermions and of electrons in wires. Okay, so...
And then there was demonstrations of the superfluidity, or...
Yeah, so there was, so electrons, however, as I've just mentioned in helium's, in Sommerfeld's theory, are fermions. So no one thought of applying Bose-Einstein condensation to electrons in metals. But in fact, that was the missing ingredient that BCS supplied in 1957. They said, well, electrons may be fermions, but pairs of electrons behave like bosons. And so the pairs of electrons, which we now call Cooper pairs, can undergo Bose-Einstein condensation. These are not the words BCS used, but this is our global understanding today. And that is the explanation for the phenomenon of that Camerlionis observed in 1911.
It's like for super phenomena, you need the Bose-Einstein condensate.
Exactly.
Superfluidity, superconductivity,
Perfect. Right.
I don't know what are the
right. Yeah. So this was there was superfluidity, also known in helium, and there wasn't and there was Bose-Einstein condensation. It was sitting there, but somehow people didn't. I don't fully understand why. Say, okay, yes, it looks obvious in retrospect. Well, maybe helium at least is a boson, and therefore there's the Bose-Einstein condensation explains the superfluidity. That's true in some general sense, but there's many details that need to be worked out. And this was all worked out, in the 60s. Landau was also important in making all these connections, and BCS and many other people. Right. So once you come to the 80s, which is when I entered the field in some way, these theories of Sommerfeld for electrons, the BCS leading superconductivity, and Landau and the theory of superfluidity, really everything seemed to be in place. Everything was understood. And the feature of these theories was that you're dealing with quantum particles. Quantum mechanics is really important, but you deal with the particles one at a time. You work out the theory of Schrödinger equation for one electron, or maybe two electrons at most, or one boson. And then you just assume that you can describe 10 to the 23 electrons by just repeating what you did for one electron. Just do it independently, and you get some collective behavior where all the electrons are feeling each other by their statistics, but not much more. And this basic idea, which I guess you can trace to Sommerfeld, was very, very successful. It explained almost everything quantitatively.
Was it so successful that at some point during that time, some people thought, oh, this is a solved problem, like the field is solved, the rest is too dirty, or everyone always knew there was more to
absolutely.
gain?
Yeah, people were also saying, okay, well, there was, the basic phases of matter seemed to be understood, I would say in the 70s. But then there was certainly a burst of progress on the topic you mentioned, the normalization group and critical phenomena. That involved some cooperation, but it was mostly associated with finite temperature transitions, where the cooperativity was due to thermal fluctuations. Quantum mechanics wasn't playing much of a role in that cooperativity. So that happened before I entered graduate school. And again, so that was probably the most exciting thing in those years. Everyone was using the normalization group and applying it to, this one domain of phase transitions, like the boiling point of water and so on, and making a lot of progress where you were going beyond the independent particle picture.
So is that what you did your PhD work?
Yeah, so my PhD
yes.
work, it involved, I certainly used the renormalization group on various classical phenomena.
And mostly condensed matter physics based, or was there also back then already this back and forth between high energy physics?
No, I was doing just classical condensed matter physics in my PhD.
Right.
And then after my PhD, I went to Bell Labs, where I started thinking about more quantum things. I mean, they were thinking about problems in semiconductors, certain semiconductors, which undergo a transition, a phase transition, a quantum phase transition, in fact, between a metallic state and an insulating state as you change the density of electrons.
Was that a difficult transition? Because you said you were only working on classical problems prior. So was there a steep learning curve when you arrived at Bell Labs to translate it to the quantum?
Well, I mean, fortunately, it was a great place to learn. And the nice thing about it was you had all these theorists sitting in between all the labs. All the people who were doing the experiments and the theorists were sitting right there. And so you would hear about, some experimentalists coming by and talking about what they were looking at.
It's an amazing setup.
Yeah.
I love
It's like
it.
these days I'm
Yes.
trying to bring
Yes.
software engineers or theorists in the same room with experimentalists.
Yes.
So, once you had something real in front of you where even though it was something you knew very little about, it gave you a kind of a direction on how to think about it.
Yes, absolutely.
and then you can go back and read the papers and talk to many other people around, and so you can learn very quickly.
Is there any experiment in particular from that time that you remember where you were like, oh, this is giving me additional insight or like a framework to think about my problem?
Yeah. Well, I was thinking about what silicon, basically the central material in all the electronics, but silicon at very low temperatures where the density of electrons was very low, and what was happening is that the electrons were getting trapped in certain regions near the dopants, as they say, and these electrons were starting to entangle with each other. There was some indications of that from the experiment. So I was starting to think about quantum entanglement of electrons and how that was influencing macroscopic properties.
Is there an easy way to explain what the signature was that might have given it away that there could have been entanglement in play?
Sure.
Dopants?
Yeah, let's see. So if you have, so imagine you have two electrons which are in traps nearby in silicon, then they'll form a valence bond. Covalent bond, or you could think of it as two electrons, forming. There's one is up and the other is down in the spin, and then there's another state where they're opposite, and this combination forms a valence bond, a singlet state. Now, the thing about this state is that it has zero net spin. So if you apply a magnetic field, the magnetization that you see is essentially zero below a certain temperature. And how low do you have to go in temperature? Well, there's a certain energy, which is called the exchange energy, below which this entangled state doesn't form. They just kind of become independent. So that energy. So what if you measure the magnetization or the magnetic susceptibility, you'd get what we call the Curie susceptibility at some high temperature, but then below a certain temperature would go to zero.
Right, so they would just sweep the temperature and see how.
Yeah, but so in this case, what was confusing and kind of bizarre was that you didn't see, the Curie susceptibility and something suddenly go to zero. You saw it kind of decrease and then decrease with a very strange temperature dependence. And so this was understood by the fact that it's the electrons actually form many different pairs. It's what's called the random singlet phase, where the nearby electrons form singlets, but then there's other electrons farther away that form singlets, and then other. So there's kind of a hierarchical structure of entanglement, which then when you work the numbers, it could explain
Like
the
the
experiment.
entanglement fractal, but probably without the
Yeah, but it was still
structure,
pairwise. You had the electrons, closest to each other would entangle first, and then the other pair would entangle, and then the other pair would entangle. So you could still build it up in, as you said, in the renormalization group, where you start with very short distances and slowly start going up. And in fact, that's how a lot of that was understood.
So then, how do you experimentally? It was done, like how are the samples controlled? Is it like the doping? How the samples are?
Yeah,
they grown, like strained silicon or something else.
This was
like
very pure silicon. I personally don't know, but they basically control the density of the phosphorus. And then you would just cool it down.
Doping, essentially.
Yeah, it was doping. That's really all you had control over. I mean, today, this is 40 years later, people make they have nanoscale control. They can take a little crystal of silicon and put the phosphorus atoms in certain places. And this is being used, this is one of the architectures for quantum computing, where if you could now controllably place
single defects,
yes,
spatially controlled.
Yes, Michelle Simmons focuses
exactly
on that.
Yes, exactly. So I was working on the same ingredient, but at that time you couldn't imagine that you'd have this kind of control. You just had a random set of atoms, phosphorus atoms, wherever they were. And so I was thinking about how would a random set of qubits, in modern language, you would say, if you had a random set of qubits at random locations, how would they entangle with their spins entangle? And you may have heard about the SYK model. That also has a similar flavor to it, and I very much owe that to the work I was just happenstance that I happened to be doing at Bell Labs when I first started as a postdoc, thinking about such random systems. Yeah.
So for this SYK model, which is Sachdev, Kitaev, the names of the developers, inventors of the theory. So how did it? Did it end up? How did you come to the theory?
Okay. So let's move. So at Bell Labs,
Bell Labs. Okay.
So at Bell Labs, I was working on these stationary trapped electrons in silicon. That's what I was doing in 1985, 86, and then one day, news came of the discovery of Bart Bednarz and Miro to Bell Labs, and so this being Bell Lab, they said, "Oh, can't be true." How can something so this important be discovered outside Bell Labs? I'm just joking.
But not really.
But immediately, there were people there who could make these materials right away, and it worked. Yes, it was true. And so there was just incredible excitement that now suddenly there's a superconductor, which is initially at 45 Kelvin, and then at 70, and then at 90, within a matter of months.
Was it also the time of this big announcements, like the low temperature fusion?
That was a bit earlier. You mean cold
was
fusion?
Was it before or after?
It was after cold fusion.
Okay, cold fusion. That's right.
Yeah, but that that had been a little before, and then it continued later.
Did you overlap with Federico Capasso at Bell Labs, or did you?
Oh, yeah, he was already there. I was only there for 2 years as a postdoc, but he had been there for a long time. I think he was there at that time too. Yeah. I think his work on these
QCLs and
that had been done before I got there.
Oh, really?
Yeah, pretty sure. Yeah.
Wow, that's because I would have thought that this came before because the quantum cascade laser is so highly designed.
That was when quantum QCL?
I don't remember the exact
year.
We
can look it up. Anyway, so then there's high temperature superconductivity, and as I mentioned, if you look at the structure of, so this is the cuprate superconductor. It has a complicated crystal structure, but all you need to focus on are the copper atoms, which are these orange sites, and they form a square lattice. It's just a very simple infinite square lattice. Here's a little piece of it. And if you dip it in liquid nitrogen and put it over a set of magnets, it can it can float because it's a superconductor. But now it's warmed up, and so then it falls down. And
so that was like big news on this lentium structure.
that was the first, and
The
why
first
we
one, and then people just started to put everything in, like take all the materials they have on their shelves. And how did the YBCO?
I think I wouldn't
horizon?
know. I mean, there's a sort of a black magic and a lot of insight that materials chemists have. I think it became clear that the copper oxygen plane is the most important. So now the question is, how do you get more of these copper oxygen planes and maybe put them near each other? And then it's a very complicated chemical question of what will fit between, it has to be atoms of similar sizes that will fit in here. And they also have to donate some electrons or remove some electrons from the square lattice. That's very complicated chemistry. So people, basically, if you have yttrium, then you go along the periodic table. If it's a transition metal, you look at elements near it, or lanthanum, yttrium, they're very near each other, I suppose.
So I can see, like, from that diagram that mostly the superconducting effects come from the cuprate lattice.
Yeah, copper
so I
oxygen.
guess like oxygen steals or donates some of the like electrons. But then what's the role of this, like the Y and the ions of yttrium and barium?
Well, they're there to basically remove electrons. So they
remove it.
Or donate. The barium becomes 2+, and yttrium becomes 2+, and then there's oxygen, which is in some chains over here. These are the chains.
Is there any simple explanation why BCO so far has the largest, the highest?
Highest is BISCO.
Yeah. Oh, BISCO. Oh, I see.
Yeah.
Is it like related to? Can we see immediately from?
No, I don't think so. I mean, that involves
that because of the I don't know, the heaviest ions or.
I think it's some very complicated combination of the chemistry of each ion and the structure. If you put in a different ion, the structure is slightly different. The BISCO, or I don't even remember the composition, is the one with the highest TC these days.
Would you
and it has certain layers next to each other, closer to each other, 3-layer, 4-layer, 5 layers, and those have higher TCs.
So how practical is this BISCO?
Well,
comparing to YBCOs as
right. So like I said, YBCO is good enough because you can do this experiment. This experiment you could not have imagined.
Yeah.
Yes, absolutely.
Before you can just put in liquid nitrogen. It's good enough.
Right.
So in practical applications, for example, in this fusion application here, where they're using, these are now wires of YBCO that people have learned how to make over several decades. These are being used by several companies, including this company here in Boston.
Yeah, we interviewed Dennis White. Yes.
Okay. Oh, great. To confine, the plasma here that's eventually, hopefully, going to produce energy. And they use YBCO, and I suspect it more has to do with the ease of making such wires. It's, this is a ceramic. This thing that's what it actually looks like.
Yes.
So how do you take a little ceramic and make it into a wire?
Yeah, it's quite
that's
brittle.
A technological industrial process. And for reasons I don't understand, somehow YBCO is the one that allows you to do it. That's why they're using YBCO.
Every time they switch on their tokamak, we see noise in LIGO.
Really? I see.
It goes into our electronics. We are in the same building.
Okay. Anyway, so I was telling you about this. So now this material, if you look at just a single copper oxygen lattice here, then it turns out before it goes superconducting, so here's the phase diagram, as you change the composition of the other ions, the density of electrons in the copper oxygen layer changes. And when you're at this, what's called hole doping P, when you're at P equals 0, then you get the state where it looks like this. So it's as if a single electron is trapped, as it was in phosphorus-doped silicon.
Antiferromagnetic, or what is it?
Yeah. So but they're now on a perfect square lattice, and when P is 0, they form this antiferromagnet where half of the spins point up and the other point in the opposite direction. So this is again a relatively simple state because you can understand it in the one electron picture. All you need to know what each electron is doing, and you just put it together. Or in this case, 2 electrons form this up-down state, and then you just repeat it infinite number of times. Okay. So this is a well understood state. Already much had been understood before the discovery of the materials, and even more things were understood about it. But the remarkable thing is, if you take this insulator and you now remove some of the electrons, so sorry, I don't have that animation here. So you remove some of these electrons, and then they can start moving around without hitting each other if there's some vacancies here. And for some reason, that system of this antiferromagnet with a few vacancies is a high-temperature superconductor. And that's,
Is there a good value for this X? Like an optimal for...
Yes. So, I mean, the X is somehow related to the P. Yeah, and P around, in this case, 0.15 gives you the highest TC of 100 Kelvin. Yeah. So this is where you want to work at these values of X that put P over here.
It's amazing that it's quite broad.
Yeah. So here's the antiferromagnet now. And then I don't look at the right-hand side. That's a bit more technical. You remove a few of the electrons. And so now these electrons can move around. But what you also notice from the phase diagram I showed you, the antiferromagnetism disappears. So you can't have this regular arrangement of up, down, up, down, up, down. It has to disappear. So how does it disappear? Well, again, you get this phenomenon of entanglement. And the idea is that near neighbor electrons form the singlet state, the state where one is up, the other is down. So in this state, the average spin is 0, and this is the valence bond I was talking about in phosphorus-doped silicon. Okay. Now in phosphorus-doped silicon, it was, these were atoms that were close to each other, phosphorus atoms, and once they form a singlet bond, they just stayed there. But what happens here is something remarkable, because now you can see that there's many different ways to form singlet bonds. You can have, these, like here, these 4 electrons can exchange partners. They can do that and that. And while they're doing this vacancy can move around. Okay, so as this vacancy is moving around, for some reason, in this singlet bond background, it's a high-temperature superconductor. So that is a very quick summary of the theory.
And I assume that for some reason, you know exactly now what that reason is.
I think, so remember, so these vacancies in general behave like fermions. And so you have to have the BCS mechanism of the fermions forming pairs and the pairs condensing. So I think everyone agrees that given this kind of antiferromagnet, if you change the density, the antiferromagnetism leads to the formation of pairs, and then the pairs give you a high TC superconductor. So that part is I think there's universal agreement that that's the mechanism, if you wish.
So in this case, like the electrical current, it's mostly induced by the movement of the holes in the...
Correct. So it's these vacancies here that are carrying the charge, because when these two resonate, see, when you look at that process, nothing is moving. The electron charge is completely stationary. It's a very subtle movement. It's just it's a motion of the entanglement. It's not something you can see
Yes.
directly even.
I wonder how one would even try and measure
Yeah, so
that.
it affects people send in neutrons and do neutron scattering, and it affects the spectrum of the neutrons that come out. This resonance
like
affects that which energy and momenta they come out.
Right.
So, but then you need some theory to compute that in detail, and that's one
Yes.
of the things we have been working on. In fact,
Oh, amazing.
And
So
cuprates,
here,
Yeah.
cuprates by its nature, just from the very beginning, it's like dielectrics, and then let's say non-conductive materials.
yeah,
So it's only when you dope them to a certain degree, then you
so that was
observe
this
that.
phase diagram I was showing you earlier.
is the diamagnetic in its normal form?
That's a very small diamagnetism in the metal. So in this, but you start from the antiferromagnet, you dope it, you introduce these vacancies, and then you get the superconductor.
But then the metal phase is only when you cross the certain degree of doping on the right.
Right. So if you were to study this blue region here, you would find that Sommerfeld's theory from 1929 actually works.
I see.
But that brings me to the original question. But if you were to look here, suppose you sit at the superconductor and you heat it up, and then you try to apply the Sommerfeld theory and the Landau theory over here, you would find it's a total failure. Okay. So this is a metal, like copper, where charges are moving. It doesn't have a zero resistance, but the way the resistance varies with temperature, and there's various other properties you can measure, how it reflects light. That's something also you can compute from Sommerfeld's theory, and you apply it here, and it doesn't agree at all with what you see. So people started calling this the strange metal. Okay. Right. So there was essentially no theory for it. And the strange metal had started to be seen in 1992 when I came up with what's now called the SYK model.
What's the signature of a strange metal to conventional metal?
So the simplest thing would be, I don't know if I have a plot here, would be just the resistance as a function of temperature. This is not quite the resistance here. This is something else. If you look at the resistance, it increases as a linear function of temperature. Just imagine this axis is temperature and this is resistance.
It looks like that.
It looks like that. I mean, but that's not what this plot is.
They're linear.
Linear dependency.
Yeah.
I always converge. to
So,
best
you
benefit.
could say everything is linear to first order. Why are you so worried about this? But you have to understand why it appears here and not in other metals. And so what we understand today, and I think everyone would agree on this, that it has to do with complex quantum entanglement, that the basic assumption of Sommerfeld's theory that you can treat the electrons independently of each other, it breaks down. Now, I've already told you a little about complex entanglement of spins, where I had these resonating valence bonds. Okay, but that again is not really, as I said, nothing's moving. That's not something you can immediately use to describe a
And
metal.
bond is only between two electrons.
Neighbors.
Two neighbors. So
Yes.
it's not a complex kind of a group bonding
right.
between all the
Right.
near term, like let's say if it's for cuprates would be, let's say 3 or 4
Yeah.
Like in
nearest
resonance.
Right. So
nodes.
so then, so the thinking in my mind at that time was, well, okay, this strange metal seems really bizarre, and and what we didn't use the word entanglement in the early 90s, but somehow we have to go well beyond Sommerfeld's theory. And we know how to go. We're starting to understand how to go beyond independent electrons, at least for these resonating valence bond type states.
How did you call entanglement at that time?
We just said,
Correlations, strong correlation.
Yeah, strong correlations.
Spooky,
Right? Yeah, the word entanglement and many-body entanglement hadn't really entered the language until I think the mid-90s or late 90s.
What about strange metal? Was it called that from the beginning?
Yes,
It was just so
yes.
strange that everyone was like, okay,
Yes.
this is strange metal. And then it
Right.
kept that name, yes.
Yeah. So my thinking was that, okay, this is what you really need is what, sometimes called a toy model, some model where it may not look like the real world, but at least it's strange.
like
you
a-
needed some
yeah.
model that looks strange.
Could you call it like a metal with like a strong exchange interactions?
Yes.
So it seems like it's all comes back to this the interaction potential or interaction energy.
Yes,
And then it
but
depends like what's the J between.
right. So here, like
spins.
as I was showing you, I have this this kind of resonance. So this is entanglement of 4 electrons, and as this thing moves around, you're entangling everything.
Mm-hmm.
But it's mostly entanglement of spins, and that's not the main thing in a metal.
Is entanglement lost when the bonding switches? Like you were showing in this animations, there will be, let's say,
No, but
when they go from like too vertical to too horizontal.
No. So it's not as if anything's moving. So there's a wave function.
Wave function. Okay.
Okay.
Wave function changes.
It's like, it's like the double slit experiment where you say the electron is both on the left and the right slit, or the cat is both alive and dead. So here, this is more like the cat. It's both this and this. Oh, sorry. It's both this and that. They're both there.
It's like in the benzene example you were.
Yes. So
Yeah.
it's just a superposition of a huge number of states.
Wow.
Not just 2 states, but lots and lots of states. It's a massive entanglement.
This is like a snapshot for one of the states, but you kind of sum up,
Right.
and you have a superposition.
Right.
of
So you have
all
one.
these
So
bonding
in the
states.
lowest energy state, you have one particular superposition. In the next excited state, you have a slightly different superposition. Associated with each state, there's a complex number in front of it in the wave function, and that wave function changes, but it changes in this many body space, not in terms of some single particle state. That's the big difference. So my thinking at that time was, can you come up with some model in which you have entanglement, but things are actually moving. You don't want to trap them and only have their spins entangled. You want a metallic state where moving electrons are getting entangled. And so that's how the SYK model works. Now, I should say, in full honesty, and what I proposed in 1992 was slightly different, but it's more complicated to explain. I'll explain the version that Kitaev came up with, or
With the Majorana
well,
formulation.
yeah. So this is actually, it is not quite Majorana, but so this is the idea. So imagine you have some set of traps. Now, of course, you would say that's nonsense. In cuprates, everything is a square lattice. But that's not quite true. There are impurities. There are these yttrium and the barium atoms. They're not everywhere. They're trapped in different locations. There's the oxygens. Sometimes some oxygens are missing away from the layers.
Perturbed lattice.
Yeah, it's a perturbed lattice, and so there is impurities there. Okay, and that's definitely playing a strong role in their physics. We know now from many experiments, and there were already some experiments that time. The people were observing some glassy behavior at low density in between the antiferromagnet and superconductor. Anyway, so I said, okay, let's put them in random positions, which is what I'd been doing before for phosphor-doped silicon. So let's take them random. And then you put some electrons in there. Here I'm ignoring the spin of the electrons. And previously you were having them form singlet bonds in some random way, but now I'm going to allow them to move in a random way. So I'm going to say, well, maybe there's a process, quantum mechanical process, that electrons on site 11 and 12 move to site 5 and 14. This is they feel each other and they together want to move. Okay. But I'm going to forbid any electron from moving on its own. If you allow an electron to move on its own, you would get back Sommerfeld's theory. So I said, okay, let's just take out Sommerfeld and just only allow them to move in pairs. And so there's
But
some
without yet knowing a mechanism for how exactly you're just putting this
yeah. So
theoretical
this was
constraint.
at that time it was okay.
Yes.
We just want any example. We don't care how ridiculous it is.
Right.
That
Yes.
you can really understand.
Yes.
And see that there's such a thing as strange metal is possible. Yeah. And so there's this process where electrons from 11 and 12 move to 5 and 14. But now you take all possible processes, you can pick from 4 and 5 to 11. Everything that's possible is allowed.
And you do it only for pairs, not for like triplets?
You
like
could also do it for
quadruplets?
triplets. That won't change anything.
Bit like a quantum
Two-body
billiard,
problem.
quantum billiard, like
but
like an entangled billiard.
Right. And so the point is that, then again, you have a very complicated wave function, which has a huge number of terms. I mean, roughly speaking, if you had 20 sites, the number of terms is 2 to the 20. And then there are quantum processes allowed where you move electrons in pairs between any pair of sites. Now, in quantum mechanics, every time you have any such process, it comes with a number in the Hamiltonian. There's some tunneling matrix element associated with that process. So this is the number U that I'm writing down. All right, so I would have to give you a series of big numbers depending on where exactly these sites are, which will then determine what these electrons do. Okay, so my crucial insight was, looking back anyway, was let's just take these to be random numbers. So this is one of those amazing things that...
Let's roll the dice.
Yes, just roll the dice. Take them to be random numbers, and then maybe you can make some progress. So now if you gave me a series of numbers and say, I want to know what this particular model does where I have these particular numbers for the U's, I can't tell you. It's a very, very hard problem to solve that. But if you allow me to just assume they're kind of random, then it turns out that the behavior of this particular system is self-averaging. It doesn't matter what the numbers are in the end. That's something we understand now. But at that time, it was only a hope.
Yes.
You just take some random numbers and the details won't matter. And in fact, we can prove, at least for this model, that they don't. Anyway, so that's the model where you just allow these to be random. That's it. That's the complete model. It's a solvable model of multi-particle entanglement. And what you find then, that it leads some very complicated quantum states whose excitations are not particle-like at all. No bosons or fermions. And the current can be carried by this complicated quantum object in what you'd say an entangled quantum soup. It's really carried by changing these complex numbers a little bit, and it's not as if you're seeing electrons go one by one. You can see them. Anyway, so that was the model.
And then the anyons is essentially, it's like the term for this multiple...
Well, okay, so this is a slide from
what do you call excitations?
Right. I mean, okay, this is jumping ahead a bit, but because of where I've taken these slides from, anyons are excitations in this fractional quantum Hall states I referred to earlier. They behave like anyons, which are somewhere between bosons and fermions in their statistics. So today we understand that anytime you have a complicated entangled state, it can have particle-like excitations like they do in the fractional quantum Hall effect or the integer quantum Hall effect, which could be anyons or bosons or fermions, anything in between. But there's a whole another type of state, like the SYK state, which doesn't have particles at all. Particles, even though, if you really looked at very high energies, look at the microscopic structure, yes, there are electrons. But you'd have to go to some really high temperature to see that. But at the temperatures you're measuring the strange metal, and at the frequencies you're exploring it with light, you don't see any particles at all. anyway, so this was a model in 1993, and some variant of this, and a lot of people have worked on this model on its own, and now it's thoroughly understood, this particular model, what its properties are. And those properties somehow, well, I can also say a bit more about that, turn out to be quite closely connected to the properties of quantum black holes.
So what was actually Kitaev addition to that? Because it seems like the
form
original paper was by you and Jinwoo.
He was my first graduate student when I was a professor at Yale, which is I just arrived at Yale after Bell Labs.
He's really lucky in a sense.
Okay, luck is a big part of all of this. I was also lucky to start thinking about this,
In your original model, so this is very didactic and very easy to grasp in terms of the concept. When you first worked on just the SY part, as you said, that's a bit more complicated, but it's oftentimes interesting for students to hear like what the thought process behind it is. Is that something that we could cover
I think that's
on a...
Well, for the application to the strange metal, the SYK is definitely better.
Right.
In those days, I was thinking about spins with random arrangements, and sometimes when you have spins in random arrangement, they form this spin glassy phase. They become very glassy-like, and the spins freeze, or they form this random singlet phase that I told you about. And I was saying, well, maybe they can form a liquid-like phase. So I was thinking more in terms of spins at that time, and how the liquid-like behavior of the spins could lead to the strange metal behavior of the mobile electrons.
But it's definitely always guided by like a physics intuition or a physics toy model. Like you don't write down the math just to see, like how oftentimes it's done in mathematical or string theory, where you're just writing down the math and that something emerges. This is more guided by a physics toy model that you have in your mind.
No, I mean, it's very easy to write down. If you want me to write down this particular model, I can write it down.
That would be nice. I mean, we've seen it, but it's good to see it from the...
I mean, I showed it. So what I wrote down in 1992, very close to what I'm writing down, but I will use the language of the pictures I've shown, because it's I've already shown the pictures.
Yes, no, fantastic. Thank you.
So you had these different sites. You had an electron, let's call this site alpha, this site beta, this site gamma, this site delta, and you had electrons going from site alpha to site gamma and beta going to delta. So the way you write this down is you have what you call a Hamiltonian, which is what you put in Schrödinger's equation to evolve the many electron state, and then you have these electron operators. You have this operator beta and this operator delta alpha, which annihilate particles on these two sides, and they create them on these two sides. And the creation operator has a dagger on it, gamma delta. Okay, and so basically, now this process happens with some amplitude, which you say U alpha beta gamma delta, and then you write down a Hamiltonian. Okay, so and then you sum over alpha beta gamma delta, going from 1 through n.
Okay, in this form it's like
this
trivial.
So you would think this is that's, you can explain that to anybody who's learned a little bit of second quantization. That's it. And the remarkable thing is that even this very simple Hamiltonian, to fully understand its properties, you need to study a little bit of quantum gravity, and some of Einstein's equations emerge in some limited form just from this Hamiltonian. So that's this kind of duality.
Was it a coincidence, or that's what you find out later?
It was something I proposed first, and then Kitaev at some very simple level, but Kitaev was the one who really put it all together and made it a complete description, including full quantum gravity. I only proposed the connection to semi-classical behavior.
So the U's are then randomly chosen.
Yeah. So basically, right. So then you think
From
of
a
it as
random
there's an ensemble of
distribution.
Hamiltonians.
Yes.
Okay. For any, these are independent random numbers. So basically, you can just take them to be Gaussian variables. So U alpha, beta, gamma, delta, star, if you make them complex, U alpha prime, beta prime, gamma prime, delta prime. If you average over all possible realizations, that's going to be some U squared times delta alpha, alpha prime, delta beta, beta prime, and so on. Plus some anti-symmetric combinations. Okay, so that is it. You could take this one piece of paper and give it to a mathematician, go to a desert island and
they would figure it
You don't need to know
out.
anything else. You need to know that these
Let them play with it.
these operators anti-commute, so they obey certain algebra of fermions. So they anti-commute with each other, and that's it. So you can tell a mathematician, here's some operators that anti-commute. Here's some operator on the space spanned by these operators, the Hamiltonian, and tell me something about the spectrum of this. What are the energy levels associated with this, and what are the wave function eigenfunctions of this particular big matrix? That is all it is.
Why do you need to have 4 sides for this alpha, beta, gamma, delta?
Well, you have two electrons are moving from
Right.
alpha. Now
a
you could
pair.
add, you could certainly add, C dagger, alpha, C beta, something like this.
Minimum 2, that's what you need. But
You need minimum 2.
Yeah,
because
it's
the-
like the youth.
the-
well,
yeah.
like not like 3, 4,
You can
10,
add-
and
you
so
can
on.
add as
and
Yeah, you're
But that
not
makes
allowed
the-
to. Two
difficult
is
to solve.
Much more difficult.
well,
I see.
it can be solved. But when you add this, then you actually at low temperatures you lose the entanglement,
Oh, interesting.
and the Sommerfeld behavior starts coming
I
back.
see.
So really the main step was, okay, suppose this is really 0 and this is random. That's all. And once you have that idea, then you have to then work through various, the various techniques of doing this average.
How
which
long
are-
did it take you then to derive the spectrum from?
Well, the full spectrum nobody knows. I mean, that's a very, very hard problem.
Yes.
But you can get details of the average spectrum to
Right.
some very high accuracy.
Yes.
And the beautiful thing about this model is that it is self-averaging. That is, you give me one set of numbers for these U alpha, beta, gamma, delta, and then I can put in a computer and I'll get some, the energy levels, this is energy. There's been some lowest energy state and then the excited state. There's a very dense set of levels.
Right.
Okay. And then you can do some little bit of binning and you can calculate the density of
Right.
states. This is the density of states as a function of energy, and you get some curve. Okay. Now, if you want to know every little energy level, then I'm sorry.
Yes.
You need to know all the U
Yes.
alpha, beta, gamma, delta. But if you just want to know the envelope, the spacing between these energy levels turns out to be of order e to the minus n, where n,
Is the
this
number
n
of
over here is
pairs.
the number of sites.
Yeah.
So that's a ridiculously small number.
Number of states, yeah.
If you really had a thermodynamic system with 10 to the 23 electrons, it's e to the minus 10 to the 23. No one's ever going to
Yes.
have that kind of resolution.
Yes.
So if you want to know everything in detail, forget it. But if you just want to know the average, it turns out it doesn't actually matter what this is. It's self-averaging. You just need one
Right.
system with one given realization of these random numbers. It'll give you the same envelope.
Right.
And also anything you could possibly measure is self-averaging. Yeah.
And then during this time, were you only looking at this Hamiltonian? Because you said that there's the connection to black holes where basically might
Yeah.
be easier to solve in.
Right. I can say a bit more about that.
Oh,
that came much
absolutely.
later.
Absolutely.
So maybe I sit down
Yes.
for that.
What's the main signature that you're like, okay, this is the strange metal thing?
Well, I think, as I said before, they measure temperature-dependent resistance.
I see.
But
It's linear.
yeah, but that is not the complete, not the only signature really. I mean, because there could be some other reasons from phonons that give you something linear. So, but there are other characterizations, in particular how they reflect light as a function of frequency. That's a much better probe, and that also turns out at some times, I think I had this picture here.
In what wavelength region is that? Is that more towards
Infrared.
the infrared.
I mean, depends on the material,
Yes.
but it's usually
It's
that's
like
what.
quite long wavelength, not like the super high energy.
Yeah,
regions.
no, it's not.
EV.
These are correct. So this is some optical scattering time you can measure from the reflectivity. And it turns out to have this behavior that the natural unit of the scattering time is just Planck's constant divided by temperature and Boltzmann constant. So it's independent of this U. And in fact, that was the first thing we discovered. Actually, I should say my longtime collaborator, Antoine Georges in Paris, had an important role in this. That we solved this model, and it looked like there were no excitations. It looked like a soup. But then you can ask, suppose I kick this model, what is its natural relaxation time? And amazingly, we found that it's just Planck's constant divided by temperature.
Oh, amazing.
So that was really the first hint to us that we were on the right track.
Yes.
Because that was what also being observed in the optical conductivity in the cuprates. And that's exactly what we see here. And this is quite remarkable from the point of view of, normal condensed matter physics.
Yeah.
So there, if you want to compute some electron scattering time, in fact, the way you do it is by the Boltzmann equation.
Yes.
But this is, again, a very interesting story. Boltzmann was thinking about, theory of gases, classical molecules in the air. And he wrote down a Boltzmann equation for how molecules in the air collide. Now, it turns out that if you now want to go beyond the Sommerfeld theory, where the electrons are moving independently, and allow them to collide a little bit, what Landau showed in the 60s was you basically have to resurrect the old Boltzmann theory and apply it to the electrons with a few small changes. And from the Boltzmann theory, basically the basic result you would get, which Boltzmann also knew, that the scattering time would be 1 over the square of the interaction strength. That is, the weaker the interaction, so the interaction is U, then the scattering time would go as 1 over U squared. The weaker interaction, the time would become longer and longer and longer. Okay. And this is seen, and if you look copper, you do the optical conductivity, you see all of this very clearly. So
I
here,
really like that. This is like very simple
Yeah.
answer. Although I don't know what is behind this.
so that was, that was the
function.
And does this
no,
already
f is again
give...
it's also a pure function. Where there's it doesn't depend on U anywhere.
Okay.
It's just a function that so the SYK model has some function f that you can compute. It's just some tang something and so on.
And does the form of the electron scattering time already give you a hint that you could do a Wick rotation on this Hamiltonian to then have this correspondence between quantum effects and statistical mechanics?
Right. So exactly. So in fact, you do imaginary time path integral on this.
Because this looks like kind of it should emerge
where
from.
the length of imaginary time is 1 over temperature. That's h bar over temperature. That's how you, and then you Wick rotate to get this answer.
Oh, okay.
Yes, but it was very surprising that you had a many-body system where you could show that the scattering time was just h bar over kt. It didn't involve U at all.
Yes.
And strangely enough, that was what was being observed. And so certainly we were very excited that this was the way to go, that the scattering time is h bar over kt. Now it's sometimes called the Planckian time. My friend who died last year, Jan Zanen from Leiden, he came up with the word Planckian dissipation. That's what this, like I say over here, Planckian dynamics. So the SYK model was the first solvable model that showed you Planckian dynamics. You could prove it.
And this only emerges if we assume that U is from a Gaussian distribution, from a
No,
random
in fact,
distribution.
it doesn't.
Or it doesn't even.
No. Like I said, well, we can prove it for any distribution as long as they're independent random variables.
Oh, okay.
That's all that's required.
So,
They're independent random variables.
So that's the only restriction you need on the U.
That they're independent.
Yes.
Yeah. Now, there's some subtle correlations. Probably that doesn't matter, but we can't.
But they're
prove
weak.
it.
Yeah, we do not.
We can't prove it.
Yes.
Anyway, but it's been a long road to go from the toy model to the real theory of strange matter. We're still working on it, but I think we're close. But not everybody agrees with what we're doing, but I'm pretty confident we are.
So then how is it applied from, let's say, this phase transition on like strange matter to something like related to gravity, I guess, black holes?
Yeah. Okay. Maybe I'll give a physical picture first. And the history of it is very complicated. But let me just say a few words about what is a black hole. So a black hole is, again, a solution of Einstein's theory of general relativity, where if you put a mass m inside this radius r, it's called the Schwarzschild radius, where g is Newton's constant and c is the velocity of light, then light can never escape from inside this object. So if you took the Earth, you'd have to squeeze it down to 9 millimeters to make a black hole. So that's how dense a black hole is. In fact, it's even more dense because the matter, once it forms a black hole, keeps collapsing down to the center.
You keep it in your pocket.
Ultra dense energy source.
Yeah, so you would think this is just pure fiction, which is what people thought in 1916.
Yes.
But it's not. There are black holes everywhere, including in the Milky Way.
And we hear them collapse.
Right. You work at LIGO, of course.
Yes.
I shouldn't be talking. Anyway, so now Hawking, his great contribution was to start thinking about what is the consequence of quantum mechanics for black holes. And his idea can be sort of phrased in modern language this way. Imagine you have some pair of entangled electrons, up, down, minus, down, up, and they are separated when one of them falls into the black hole and the other one stays outside. Well, quantum mechanics, they're still entangled. That is, if this is up and the other is down, vice versa. But if you're an observer here with this in your hand, there's no way you can know what the other one's doing. So to a very good extent, in your observable universe, because you can never communicate with the object inside, this is a random spin. It's not entangled with something else. It's totally random. But we know from Boltzmann that randomness is entropy. So that's a very quick argument that why black holes have entropy. Okay. This simple picture of some entangled pairs around the horizon. And in fact, from this kind of picture, Hawking was actually able to compute the entropy of a black hole. That's S, is the area of the horizon, because that's the number of entangled pairs. And then the rest of the velocity of light, Newton's constant, and Planck's constant. So this is already, first of all, kind of amazing. This is telling you that black holes are not really black. There is some contact from the inside and outside through quantum tunneling and quantum entanglement. And also the entropy is proportional to the area, not the volume. Mm-hmm. So, the entropy of your coffee cup is proportional to volume. Everything is entropy is proportional to volume because that's the number of random degrees of freedom you have. But here is the area, and that's because it's really due to the entanglement across the horizon. Anyway, so that's the picture, but people have been trying to understand more details. What happens when the black holes start evaporating like your coffee cup, and how does the entropy evolve, and what do the excited states look like? And what's become clear is that this is too simple a picture. A better picture is this. That it's really it's not pairwise entanglement of pairs. It's a very complex entanglement of everything entangled with everything else, like in the SYK model.
That makes sense.
So from the outside, for certain black holes, any black hole with a net charge, in fact. So if you're an observer outside and you're looking at the black hole, to very good accuracy, you may as well assume there's an SYK model sitting there. I'm not saying there actually is,
Yes.
but it captures all the right physics. And all right, so the fact that this might be the case was something I proposed in 2010. And the reason for it is the following. This is something also you might know from LIGO. So if you have when you take LIGO observes the mergers of black holes, and there's something called the ring down time. When a black hole, two black holes, they start and they merge, and then eventually they become a perfect sphere. Okay, so that ring down time can be computed from Einstein's equation. But if you just write the answer in terms of Hawking's black hole temperature, the answer is in fact exactly the Planckian time. So the black holes have this feature that they relax to equilibrium in the Planckian time, which is exactly what the SYK model does. So in fact, that's what's special about the SYK model. You could take any other model, and then now there's many others. I'm not saying, and they're all equally good, really, as long as they share the feature that they have complex entanglement with a ring down or equilibration time, which is Planckian. That's the key feature.
So what's on the order, the way it ranges the ring down time? Or like also, I guess, depending on the
It just depends on the Hawking temperature. Yeah,
I'll say maybe for like what have been observed for the black holes.
Milliseconds, I think.
Yeah.
Right. Yeah.
I mean, the frequencies is around 100 hertz, and then it does this chirp.
Yes, at the very end. Yeah, I don't have a picture here, but yeah. So there's been in fact, people have cataloged a lot of these ring down times from LIGO, and there's a paper in Physical Review Letters showing that they are all very close to the Hawking h bar over kT time.
Yeah, there's a recent paper also that shows that the area theorem is satisfied.
Yeah, that's a little different, but yeah, this is yes, exactly. I saw that. Right. So I had been learning that's for these via this ADS CFT duality, which is the original connection between complicated quantum systems and certain special black holes. I'd been learning a lot about that. And while I was learning about non-special black holes with a net charge, that is not supersymmetric, I learned about some of their properties, including their ring down time. And these properties look exactly
so eerily similar.
Exactly. And at that time, I would say I was the only person in the world who still remembered the 1992 paper and also knew a little bit about black holes. I said, these look almost exactly the same.
What compelled you to look into black hole physics? Just curiosity?
No, there's a whole long story there also, which I don't know if you have time to go into.
We would love to hear, because that's the things that typically you don't see in papers, right? But it's interesting to know.
Right. So the origin of this is this so-called ADS CFT duality. I think you've talked to Juan Maldacena in your series, right? So he came up with this ADS CFT duality, which was a duality between certain supersymmetric black holes and a conformal field theory. That's what CFT is. So, I mean, you can think of SYK model as also sort of a conformal field theory, but it's in zero space dimensions. But Maldacena was looking at conformal field theories, supersymmetric conformal field theory in 3 space or 4 space dimensions. So much more realistic, but very, very complicated and very special with a lot of supersymmetry. Anyway, but this gave a handle on understanding in finite dimensions, not in 0 dimensions here, certain very strongly entangled quantum systems. And so, the criticism I got in 1992 and many times since was, this is all very nice, but who's going to believe that the cuprates have anything to do with these random hoppings? That doesn't look like a square lattice at all. And fair enough, this is fair criticism. So I was thinking about other cases where you didn't have to go to the 0 dimensions and have these random couplings.
Right.
So in some sense, the Maldasena's work is the exact opposite. It's got huge amount of symmetry. It's very, very special, but it has no randomness, and it's in 2 or 3 or interesting spatial dimensions. Yeah, so
but
that
what
was
caught your eye about ADS CFT theory? Why were you looking into
well. So
it?
I wasn't. I think the reason was not so much the cuprates, but experiments in cold atoms, for example, where they were measuring the transition between a superfluid and an insulator. Maybe I can draw that. That's actually
that's
that would be
simple
great, yes.
thing to draw that relates to some of the
Thank
things.
you.
And I think it's related to what I was saying earlier, that there was a revolution happening starting, in the late 80s, where suddenly people started thinking about, what happens to quantum mechanics when you entangle large numbers of particles, not just 1 or 2, but infinite number, really. And in some ways, string theory is also a tool that allows you to do that.
Yes.
But that's amazing that this is the kind of a close contact between the quantum theory and gravitational theory, and which you can measure also on the experiment. So it's not like some string
we can measure
derivations
that,
which are
no one's seen
cool,
the
but
no one's seen the fact that the radiation is quantum in black holes has not been seen.
Yes, that's true.
It's you have this time which is of the right order of magnitude, but it's still very
the smoking gun, let's say.
Yeah, I mean that's the main reason Hawking didn't get a Nobel Prize, I think,
Yes.
because it's never really been seen. Well, okay. Anyway, so this is not quite the cuprates, but it's related. So now today people make optical lattices. So you just think of it, you have a bunch of atoms. Rubidium is the atom they often use. They're trapped in some magneto-optical trap. And by sending in lasers moving in different directions, they can have the atoms experience a periodic potential. So this is some potential, this is X, and this is V of X. Okay, and then they load this trap with some atoms, and so these are rubidium atoms, say, and they repel each other, and so one atom sits in every well, for example. Okay, so now if you have this configuration, so there's 2 different energy scales to keep in mind. One is the depth of the potential, roughly speaking. Let me call that W. And the other is, suppose a rubidium atom sat on top of another atom on the same site. They will have a repulsive energy, which I'll call U. So I can try to plot what the atoms are doing as a function of U over W. Okay, and these are bosons. Okay, so then what happens at large U over W, when U is very large, this would not be allowed, and the atoms would all stay away from each other, and this would be what you'd call, and you'd have one atom on each trap. You see, adjust the density, so that's the case. You'd have an insulator here. Now, in the cold atom system, they can actually tune the values of U and W. You can't do that in condensed matter. And so now let's make U small. So when U is small, these atoms will start to move around, and one of them can hop over here, and this could, you can put 3 on a site or 2 on a site. There'll be lots of atoms moving around. And in fact, when U is 0, these are independent bosons. And independent bosons, we know, form a Bose-Einstein condensate. So on this side, you'd get a condensate, which you'd call a superfluid. In this case, would be a superfluid. So this has been seen, and there's some very sharp transition. Emanuel Bloch is famous for having observed this first. So it's a quantum phase transition between a superfluid and an insulator. So, this is similar in some general sense to the transition between an antiferromagnet and a superconductor for the cuprates, but it's much, much simpler. It has bosons. It doesn't have fermions. It doesn't have any spin. It doesn't have any dopants. It doesn't have any vacancies. It's really
It's a beautiful
it's
system.
a theorist
yes.
it's a theorist delight. And so this has been studied, and it was understood, not by me, that this critical point here is a conformal field theory.
Right.
So I have been one problem I've been working on a lot was what here it's a superfluid, here is an insulator, and we kind of understand how the current would flow. But what if you write at this point, what would the conductivity, which you call sigma, look as a function of frequency? Okay. So this is what I was trying to understand at this point. So you sit at this point and you ask, what is the conductivity? So this kind of thing has been measured now, not so much in colatoms, but in graphene, for example. But let me use this simple example to talk about it. So the question was, what is the conductivity looked at this conformal field theory point, which we also had understood, but there's no exact solution, that it has no particle-like excitation. So it shared some features, in fact, with the SYK model, like Planckian dissipation and no particles. But we didn't know how to compute anything, really. I mean, it took some effort, but we had some ideas, but we couldn't certainly compute it with total confidence like you could for the SYK model. But it was much more realistic. It was actually describing real experiments. All right, so it's a CFT, and so that's when I was thinking about this, I learned about Maldaceno's work of this ADS CFT duality. And I said, okay, well, let me start thinking about, let me see what that's doing. So let me take their CFT, which is highly supersymmetric, and see, can you compute the conductivity? And what I learned from people in string theory community was that, in fact, you could. So this ADS CFT duality, which was invented for some other reasons, for understanding black holes, suddenly was very, very useful to address this question: what does the conductivity look like as a function of frequency?
I see.
And so, so that's when I started learning about black holes. So suddenly, black holes came out to be a tool to address questions of relevance to the superfluid insulator transition.
Which is mind-boggling, because you would rather think that we use something that we can make on Earth to understand something that's like far out in space.
All of this happened around, I don't know, 2007, 2006, and I was working on this around the 2000. This is 10 years after SYK. I'd almost forgotten about SYK by that point. So I started, through this connection, thinking about superfluid insulator transitions as another route to understanding the cuprates. Started working on what this looks like, and in fact, it has Planckian dissipation, h power omega over kBt, and looks something like this. And in fact, this whole curve you could compute in some of the Maldaceno's theories. You could just compute it exactly. So that impressed me a lot. But it was again another toy model, highly supersymmetric.
Right. Was it because he was able to obtain integrable system out of it to make it computable?
No. It's in fact, this is the opposite of integrability.
Oh, okay.
This is, that's the amazing thing about the SYK and this duality, is that it gives you exact results for chaotic systems. The highly chaotic system, they're not integrable.
Right.
So that's what the power of the duality is, that you can take a highly chaotic quantum system, and its dual turns out to be a theory of gravity near a black hole. But you just have to take semi-classical gravity.
Right.
So some of the great deal of chaos in strongly interacting quantum system resembles the chaos you get naturally from Einstein's equations near a black hole when you quantize them. So
this is where you get to the Lyapunov saturation.
Right, the out-of-time order correlation function and so on. Yeah. So these are all common features between this CFT, SYK model,
which is another smoking gun that there's.
Right. I mean, it's closely connected to this Planckian dissipation.
Yes.
So I was thinking more in terms of relaxation times and dissipation and ideas on chaos. I wasn't using that language, although it's very similar. When I say there are no particles, it's a mess, it's a soup. Okay, that's chaos, right? But the out-of-time autocorrelations I'd never heard of. But Steve Schenker in particular played an important role in bringing ideas on chaos here.
Right.
And unifying all of these things. That's, yeah.
Maybe just briefly for our listeners who are not aware of the ADS CFT correspondence, because we have a lot of different backgrounds of listeners, maybe you could just briefly explain what the anti-de Sitter space or conformal field theory. So just like the very high level thing, what that is.
Right. How should I do that? So imagine you have some, here's a plane. This is really two or three dimensions, and you have a whole bunch of particles in here, which are interacting strongly and forming some quantum soup, like in the SYK model. But now, not necessarily random interactions, but really in a plane. They're not just hopping everywhere, like in the SYK model. This is in the ADS CFT, this is what you call a CF, conformal field theory, which has a great degree of symmetry, and so it's a highly chaotic entangled quantum state. So in string theory, the way you describe such a conformal field theory is what they call a brane. So basically, you can think of it as there are strings, that each of these particles is really the end of some string. So the way string theory would describe this is to say that your particles really are the end of some string. Now, as a poor condensed matter theorist, I would just use the particles to describe them. The string theorists come along and they say, no, maybe in some cases, it's better to think of the particles as being at the ends of a string.
Yeah, they're attached to the strings.
Right. And these strings, the way they connect up here is actually is what's mediating the entanglement. I mean, it's
like marionettes. There's like invisible strings pulling them around.
So where do these strings live? Well, they live in some emergent direction. So there's a new direction. So you had some coordinates x, which are your physical coordinates. So you're working in, say, d dimensions. So there's a CFT in d space-time dimension, so 2 + 1 or something. And so you want to solve the quantum mechanics in d spatial dimensions, and you don't know about strings. But the string theorists come by and say, no, you're really living in d + 1 dimensions. And these strings are hanging out in this extra dimension. And so why don't we write down a string theory why don't our theory for these strings in d + 1 dimensions? And so that's what Maldacena achieved. What he showed was there was some very specific case where you could identify the CFT here in d dimensions and also identify and solve the string theory in d + 1 dimensions. And the supersymmetry played a really important role in that. So from what Maldacena showed was that this extra dimension was in fact curved. So people often draw this kind of curvature. And so this space is what's called anti-de Sitter, and that's representing the curvature of the space, and it's in d + 1 dimensions.
So it's like a hyperbolic or...
Yes, yeah. It's basically the Lobachevsky space is the ADS2, basically, the simplest case. And that's in fact dual to the SYK model. Anyway, so you can solve gravity in ADS2 or ADS d + 1 or string theory, and that in this limit that Maldacena solved, the large n limit, in fact, you can ignore the strings and just do gravity. These strings also emit gravitons, and so they interact with each other, and that's what curves the space. All right, so that's my simple intuitive understanding. But so where does black hole come in? Well, it turns out that if you now take this CFT and raise it, look at finite temperature, look at some excited state, not the lowest energy state, Well, if you look at an excited state, that's at some temperature here. So this is a temperature T. Then in the string theory, you get a horizon. You get a horizon here. And its Hawking temperature of this horizon is precisely the temperature of the CFT. So thermal properties, excited state properties of this CFT are then related to what's happening to the horizon here at the same temperature. Yeah, so that's the connection that came out of ADS-CFT that I learned about from Maldacena and Damson and other people. All right, so this was for the supersymmetric case, and then in work with Sean Hartnell, we started thinking about charged black holes, which are not supersymmetric. And then the horizon is somewhat different. You get an ADS2 in that case. And that's when a lot of the detailed properties started reminding me of SYK model.
Yes.
So what I had done in 92 suddenly started becoming relevant to what I was working on in 2007. And that's when I realized that even the SYK model was another example, it's a very different example though in some details, of the ADS-CFT duality.
Of this kind of duality.
Yes,
Yes. That's amazing.
Yeah, and that actually, I mean, it went both ways. So once this duality became clear, especially from the work of Kitaev, so initially here, we were learning more about the CFT from gravity. So string theorists were teaching new things to condensed matter people.
Yes.
And then even with the SYK model, they taught us, once the connection became clear, we started learning new things about the SYK model. But we learned a lot of new things about the SYK model that also led to new things in string theory. I mean, so there's been a lot of work in the last 5-10 years of understanding black hole evaporation in great detail. And a lot of that is built upon insights from the SYK model. So it's information has been going both ways, and that's been very exciting to be part of.
Does it mean that you can loop in experiment then at this point? Because if you have a strange metal, you can observe certain things experimentally, and because the math maps.
Well, if you had a strange metal which is described by the SYK model, that would be correct.
Yes. Okay. Yes.
But, as I mentioned earlier, for the cuprates, no, it's not quite the SYK. It's definitely not. But it's a cousin of it in many different ways.
So far, there is no exact equivalent of the.
Well, people are trying to build an SYK model. So a lot of,
that's exciting.
We have these quantum computers now. And,
yes.
So there've already been several papers of people using IBM or Google's quantum computer to build something like the SYK model.
Like by Maria Spiropoulou, and I think your colleague, Daniel Jaffer.
Daniel Jaffer is right,
yes. Yes.
So now, since quantum computers are ramping up in terms of functionalities, what are your thoughts on how to use quantum computers for moving forward some SYK or maybe some other
or cuprate physics? I think it's certainly very, very useful. I think, quantum computers have one disadvantage in that they're dealing with qubits, which are bosons really. They don't have fermions very naturally. They're not like electrons that move around and obey the exclusion principle. That's a feature that doesn't exist for quantum computers. You have to build it in. I mean, this fermion nature. That involves some overhead. Now, when I mention this to people in quantum computing, they say, oh yeah, that's just a power of n or something, or n squared. We don't care about such things because we only care about e to the n.
Yes.
Well, okay, fine. But even, with the limited size quantum computers we have, a power of n is not a trivial thing.
Yes.
So there's a lot of overhead to overcome for quantum computers to get fermionic systems and then study complicated interactions between the fermions.
Is anyone working on this from the experimental side? Or
absolutely, There are all quite a lot of people are thinking about exactly
how to like these type of fermionic systems.
How do you implement fermions in the Hubble model, which I Yeah, the kind of model I mentioned with the periodic
Yes,
potential, but
yes.
for fermions.
Right.
Certainly, people are trying with quantum computers. But on the other hand, there are these optical lattices. You can just choose, instead of rubidium, if you choose a certain isotope of lithium,
Yes.
it's naturally a fermion.
Yes.
And those kind of experiments are going on right here in this building
Is
by Marcus Greiner.
Marcus Kleiner.
So he does
Yes.
optical lattices of fermions.
Does he use lithium?
Yes, yes.
I mean, it makes sense. It's the easiest.
Right. I don't know the details of why lithium works, but okay.
Yeah.
He has a quantum gas microscope. So
Ah.
so it's more like it's not a digital computer yet. It's more like an
Analog simulator.
Yeah. And his results are having a big impact on the theory of, they're really connecting closely to quantum matter.
Yes.
Google's quantum computer, well, it's an amazing technical achievement, but so far impact on quantum matter is relatively limited. But let's see, they're so rapidly improving every year. So let's see. But there's a new game in town these days, which is machine learning and AI.
I would like to hear your opinion on that. So, for instance,
so far they are racing ahead.
Yes,
That's really, right now, that's where the excitement is in terms of quantum materials, is how is AI going to influence quantum materials? And I think there's definitely a lot of scope there.
So where do you see its largest contribution? Because in a way, looking for these room temperature superconductors is a bit more like Edison finding the right material for the light bulb. Is this just a lot of trial and error, which we can then pass on to the AI models to do, or
well, there are many people doing that. They're exactly. So you can do a calculation for one crystal structure, and then you feed it to the AI model, feed a lot of data, and ask it to improvise and look for other solutions and so on. So I think there's a lot of people doing that. There's a company, I think, called Periodic Labs, which is actually doing experiments that they with robots and then going to feed it into
AI. They just came out of
right. But let's see if that works. But I think where things are already starting to work is slightly different way of using AI. It's not AI as such. It's really more like neural networks. You're using the neural network architecture.
It's like tensor networks, essentially. Or, essentially, like what's the killer application of that?
Well, I would say,
way of computation?
So of course, there's been already the protein folding problem.
Yes.
That's won a Nobel Prize.
But for condensed matter, like for quantum phase transitions.
Well, I would say, understanding ITC would be certainly a killer problem that you could. I think many people are now using AI methods. So what they're using is, even for the SYK, people are trying now. So you have this incredibly complicated wave function which you have to optimize.
Yes.
And that's what AI is, right? It's an architecture for optimizing. You give it, English Hindi dictionary, and it then immediately knows how to learn it, and it optimizes.
You give it SYK model and let it.
Or
maybe even more complex.
No, you use the neural network to write down a quantum state. You write down a big wave function, and then you use the AI architecture to optimize its energy.
But the Hilbert space is huge, so
it's huge.
Like, do we have enough of the knobs to adjust that?
But somehow, I guess that's the mystery of AI in a sense. Somehow, if you write things in this layered neural network with these transformers, somehow that just somehow seems to learn very efficiently, and you're able to search.
Do you think, maybe like combining quantum simulators to do some maybe random experiments, collect the data, and then
that's also people. I'm sure
let the AI models to.
I think there was a paper by Google.
Any patterns.
Yeah, I think there's a paper by Google doing just that recently. So things are really changing very rapidly.
Is it something that you personally also use, or one of your students?
I don't know enough. I'm trying to learn.
We're in the same camp. We're also we would like.
But I am collaborating with people. Especially young people who all seem to all know it.
Yes, everyone loves it. Yeah.
So you have to key is to find
Yeah.
right, young people to collaborate with.
Because so far, for instance, at LIGO, we haven't found much use for it apart from maybe signal.
Analyzing the results.
Yeah, analyzing the results. So the best use we found is to actually write a GPT for our large documentation server. So we can talk to like the millions of files we have produced.
Right.
But
So
that's
I mean, the one problem that so far I think AI is starting to make an impact now is like I showed you this phase diagram of the cuprates. You change the density P, and at some density is go from an antiferromagnet to superconductor. So you could take a simple model and ask, what is that density? Can you compute it? And I think questions like that, AI is suddenly, I think, just in the last year, starting to make progress on.
It depends how reliable are the answers.
Yes, right.
How good are its models?
Yeah, how do you evaluate it? Correct. Yeah. No, I mean, in this case, you have this wave function with billions of parameters, and you just minimize the energy. So you get an energy, and if your energy is lower than anybody else's, you're better.
Yes.
So for the ground state, lowest energy state, you have a very clear diagnostic. Your energy is better than anybody else, so it's got to be a better wave function.
I see. Easy to verify. Give me a solution.
But for the excited state, it's not so easy. You get an answer and you don't know whether to believe it or not. Yes. But at least for the lowest energy state, at zero temperature, what happens as a function of some parameter? Where is the quantum phase transition? I think these are questions that AI is starting to have a big impact on now.
What are your thoughts on the wormhole in a quantum computer paper? As someone who's not like directly
I wasn't direct. I mean,
in the field
Well, I think the consensus is that there was too small a system to really be conclusively identified as a wormhole. I mean,
I think Daniel Harlow wrote a piece in the New York Times where he was making that point that the system was rather small.
Yeah. So, but I suspect they're working on the next generation, and I'm not sure what the status is, but I'm sure we'll hear something. But there's, like I said, I think putting Fermi on this is tricky, and they need to look at larger systems. But the idea is correct. I mean, there's no question that, that if you were able to get qubits large enough with their approach, that you will get wormhole-like behavior. I don't think there's anything wrong with the idea.
Yeah,
it's just that the implementation so far is not a complete story. That's
To what degree do you think quantum criticality plays a role in this whole high temperature?
I think it plays a key role.
Plays a key role. Could you expand on that?
Well, one is the strange metal is a quantum critical phase, and we understand it from it appears at some intermediate density. So you have to look at the metallic states. Let's see. I think I had a picture of that earlier. Let's see. So here you have the strange metal, and then there are these pink and blue regions, which are also metallic, but they're very different metals. This is a Sommerfeld metal, plain old Sommerfeld metal. This is sometimes called a pseudo gap. It's a metal where the number of carriers is very small, just the vacancies. So here it seems like only the vacancies are moving. Here it seems like all electrons are moving, as in Sommerfeld's theory. So then you can ask, well, of course, if at low temperature, you seem to have a superconductor. You have a superconductor.
Yes.
But imagine you could somehow ignore the superconductivity for a while. Then there's a quantum critical point between these two metals. And I think many current approaches to the strange metal are built upon understanding this quantum critical point. Okay. So that's one role where quantum criticality plays. Then in the pseudo gap, there's also a background of spins resonating. So the pictures I showed you were too simple. It turns out that these resonating spins also have a critical nature. They have very long range correlations with them. And so that's also a quantum critical state that's needed to understand even the pink region.
I jumped
Yeah.
a bit the gun. Maybe you could, for our listeners, just briefly explain what quantum criticality is, like the critical point at T0 and your fan.
Sure.
Yes.
Yeah, you can almost see the fan here, can't you?
Yes.
Between the red and the blue.
And we're the fans of your
Yes.
fan.
Yeah, so there's a fan. The strange metal is the fan between. Yeah, so I mean, I can go back to the
Thank you.
superfluid insulator transition, right? I just drew the line here, which I can put again. Line between a superfluid and an insulator. So here the atoms were fixed, and here the atoms are moving around, empty sites and so on. This is the super. Okay, but now imagine I put a temperature, and this was the CFT that I mentioned for this case. Well, so I was saying, well, you have to figure out what's happening to CFT at finite temperature, meaning that I just take this point and raise it to temperature, raise it to finite temperature. But it turns out that it's really actually a fan like this. So here you have a critical point, which is described by the CFT, and it controls this fan-like region where you have quantum criticality, and ADS, CFT, and SYK, and all these things apply. So at finite temperature, you don't have to be sitting right at the critical point. You just have to be sitting somewhere in this region, and you will see the physics of this very complicated, chaotic, entangled state, and its excitations play out. Yeah.
Is there some easy way to understand why the quantum effects at T equal to 0 bleed out into the higher temperature region? Is it all just a result of entanglement?
Yeah. So here, on either side, I mean, there are it's the quantum effects are describing these phases. It's just that the quantum mechanics ultimately at long distances looks quite simple. You just have some independent particle description of these phases. Okay, so suppose you're at, some finite temperature. Now, if you were right at the critical point, okay, then fine, you'll see the critical behavior. But suppose you were here. Well, if you're a little bit away, then in finite temperature, you have there's kind of an uncertainty. Temperature itself gives you some uncertainty how precisely you can measure things.
Right.
So if you're in this region, you can't really tell whether you're on this side or that side because there's some uncertainty due to temperature itself. So that's why, so you behave as if you're critical because you don't have the resolution to decide which side you're on.
Oh, that's a really good way of thinking
Yeah.
about it. Yeah.
Yeah, you don't have the temperature kind of decreases your resolution, your precision.
Yeah, it
of
smears
how
out
you
the
can measure the
thermal
state.
state of
Yeah, it's
your...
a thermal state, so you
Yes.
can't measure it that accurately.
Yes.
What the ground state is, and so when you're here, you can't tell whether the ground state was on this side or that side
Right.
in this entire region.
And it's actually useful. Yeah, because usually that makes, like in our case, that makes everything kind of harder, like because we want precise measurement, but here it's actually helpful.
Yes, yeah. I mean, it wasn't totally obvious, but this is something that slowly people started to realize when they started thinking about the role of temperature near quantum critical points. But then in this regime, you get, that's where all the black hole physics comes in.
Yes.
So in the black hole, there's a horizon, which is then the Hawking temperature of the horizon is determining the precision with which you can
Yes.
identify the state. Yeah. All right. So the question is, what is holography? Well, I had this picture of particles moving in a plane connected by strings. And so you could either work with the strings or you could work with the particles in the plane, and you're describing the same phenomena. Okay, that's a very global way of thinking about it. Okay, why is it? Well, it's the word holography. I think it. I don't know who introduced it. I think maybe at Tuft or Susskind. It has to do with hologram. So what is a hologram? a hologram is a two-dimensional representation of a three-dimensional image. I mean, you have a hologram and by shining light on it, you can create a three-dimensional object. So it's a connection between two different representations of the same information, but they live in different dimensions. So that's and holography shares the same feature. You have gravity theory, which is living in d plus 1 dimensions, anti-de Sitter space, and then you have the conformal field theory that's living in d dimensions, and that's so that's the origin of holography. So the simplest example of holography, although some of the details are different, is precisely the SYK model. So the SYK model had particles hopping from here to there, but they were all confined to some region. So in fact, since any particle can go anywhere, it's as if they're in zero dimension. It's clearly a point. So it's in zero space and one time dimension. Time is included. We're talking about space-time. So the SYK model lives in one dimension, one space-time dimension. So by the principles of holography, the dual theory would be ADS2, which would be in one space and one time dimension. So how does that happen? Okay, so that I kind of explain. This is sometimes called SYK ADS2 duality. Okay. So suppose I have a black hole, in let's say in three space dimensions. So this is we're living in our space. So this is a black hole here in 3 plus 1 dimensions. And then you're an observer sitting outside the black hole, and you're trying to do something about the quantum theory of near the horizon. So here you'll have two directions. One is the radial direction r, and then the transverse direction x and time. Okay, so x is two-dimensional, that's the surface, and there's one dimension, which is radius. Okay. Now it turns out that for a charged black hole, and this has to do with some strange features of Einstein's equations, for a charged black holes, when I look at the fluctuations, the quantum fluctuations of the horizon, fluctuating of space-time itself, the fluctuations of this direction end up costing quite a bit more energy than these fluctuations. These are very low energy. So you can actually ignore the x direction. So you can, in fact, for a charged black hole, you write down quantum gravity in two dimensions, and the dimensions are r and time, just r and time. Okay, so and this space here. If you look at the nature of the space in r and t, it turns out to be exactly ADS2. So there's one space, one time, and has a certain negative curvature. This is in fact precisely the hyperbolic space.
And it's a Reisner-Nordström black hole.
Exactly.
Right? Yeah.
Okay, great. Yeah, Reisner-Nordström black hole has this feature. All right, so people have thought about the quantum gravity on ADS2, but didn't really work it through completely until the SYK model came around, and and then subsequently Kitaev made a very complete theory of the connection between the SYK model and ADS2, and then people were able to re-examine quantum gravity in ADS2, and what they found was that you could actually reduce the gravity to some fluctuations that were really essentially at a single point. I mean, basically, I don't know how to make that less technical. I'm sorry, I can't.
But sometimes
so you can explicitly.
Yes.
I mean, it turns out that you have a quantum field theory living in one space and one time dimensions. But because of the curvature of the space, all of the interesting things just happen on the boundary. And so it's as if there's a boundary, on the boundary of ADS2, there's an SYK model sitting there. Then you can, amazingly, the equations that you get to solve the SYK model have features that are essentially identical to the features you get by doing quantum gravity on ADS2. Actually, I think I can, maybe if I, let me backtrack. I've been trying to explain another feature.
Absolutely.
I think this will be, this will be, maybe I can even do this. So, all right, so one of the key features of Einstein's equations is called, which motivated Einstein's theory of gravity, is space-time reparameterization. That you have some coordinate system for space-time, but everything, it's all a fiction. The only thing that matters is the curvature, and so you have to make your theory for gravity what he called general coordinate invariance. It doesn't matter what your coordinate system is. It's really a theory about invariant features that are independent of what particular coordinates you use. You could use spherical coordinates or Cartesian coordinates or anything. Everything should be invariant of the coordinates you use, and fluctuations of curvature fluctuations of space-time are what give you gravity. This is what Einstein's amazing insight. All right, so now we are solving the SYK model. Okay, and we don't know anything about Einstein. And when you take the model that I wrote down earlier and you solve it, you get certain equations for the Green's function. So the Green's function is a function of frequency, and you can also Fourier transform it and write it as a function of time. So what is the Green's function? Well, it's something that physicists use to solve many-body systems. It tells you something about the amplitude for taking a particle from at time t equals 0 and moving it somewhere else to time t, something like that. So in the SYK model, after you do all the averaging, you get some very simple looking equations for the Green's function.
So Green's function is for a single particle, right?
Yeah, exactly.
And then you apply this to the whole ensemble.
Right. So what does the Green's function look like? Well, the Green's function generally obey what's called Dyson's equations. The Green's function is 1 over frequency minus some energy minus some self-energy, which comes from the interaction of all the other particles. And it turns out the simple feature of Dyson's equation of the self-energy is the energy of E is the energy of a particle, omega is the frequency at which you're observing it, and sigma is the self-energy from the interaction of all the other particles. So this sigma is a very simple equation. Sigma of t turns out to be minus mu squared g squared of t g of minus t. So these two equations were first written down in my first paper in 92. He wrote down this equation and I thought, okay, this is so simple, somebody must have solved these equations. And no, nobody had solved the equation. I did a search. I said, okay, we can solve it. It looks simple enough.
And back then, the search was going to the library and looking through everything.
Yeah. Oh, you ask your friends, and have you ever seen these equations before? No. Okay, this looks simple. We just put it on a computer and we can solve. Or we can do some analysis, and it's just some nonlinear differential equation. You can solve it. We solved it partly in that first paper, but we've been learning more and more about the structure of these equations. And today we know that to fully understand the structure of these equations, you need quantum gravity. So
that's crazy.
Okay, so why does that happen? So let me just let me try to illustrate that. So it turns out that at low energies, so let's actually rewrite Yeah. So it turns out at low energies, you can actually drop these two terms here. And why is that? Well, it's in simple terms, it's simply, what the energy of any particles, if the particles are interacting so strongly with each other, what the energy of any given particle is doesn't matter. What matters is the interaction with everybody else. That's far more important. So it turns out at low energies, you can just drop these two terms. And if you drop these two terms, you can now rewrite these equations in a very suggestive manner. So let me do that. I'm going to rewrite the SYK equations in a simplified manner. So there was the equation I already wrote down, sigma of t is minus u squared d squared of t g of minus t. And there was the other equation, which was after you drop those two terms, you can write it as g of omega, sigma of omega equals minus 1. But I can now write this in time space. And in time space, this looks something like integral dt g of t of t prime g t minus t prime sigma of t prime minus t1 okay equals minus delta of t minus t1. I may not get all the signs right here.
No problem.
Okay, so you have these innocuous looking equations for two functions, sigma of t and g of t, that describe the low energy behavior. And these equations now turn out to have a remarkable property. And the remarkable property is time reparameterization invariance. So this theory, even though initially, there was a clock, a preferred clock, set by the interaction between the particles and the Hamiltonian that you had, that gave you a clock. But when you take the low energy limit, it doesn't. There's no preferred clock. Time can run. You can have a faster clock and a slower clock. The equation will be the same in every frame. This is the same true in Einstein's equation too. You do a general coordinate transformation, you get the same equations. So that's in fact a property of these equations. So you can, you can take some. You have two clocks. You have a t clock and a sigma clock. And in the t clock, you have a Green's function g of t. And in the sigma clock, you have some Green's function g tilde of sigma. And, so t is some function of sigma. So this function tells you how to relate the two clocks. Then you can also relate the two g's. It's basically this, and then some power of f of sigma over here that I won't remember. From power like 1/4 or something appears. So anyway, there's a time premise. There's a way to do a coordinate time transformation. That is, you can have one clock and two clocks. You can go from the theory in one clock and the other clock. They can be running at different rates. You'll get the same equations. And this is the connection to gravity in some sense.
Yes.
This is why gravity comes in.
I see, yes.
Is this time reparameterization symmetry. But from the condensed matter point of view, what is this time reparameterization symmetry? Well, it's exactly this Planckian dissipation. We found that the only time that matters was 1 over temperature. H bar over temperature. Okay, so temperature does set a clock. It's like the horizon of a black hole is, it's something very special there in space-time, and so it does set some time scale that you have to work with, but no other time scale matters. All the short time scales associated with the U's just disappear. Okay.
No,
I don't know if I can get better than that.
This is very useful.
Yeah, but it's really the deep connection is the emergence of this conformal symmetry and the time representation invariance in the low energy theory, the SYK model. And that is a feature it shares with gravity.
Yeah.
No, I have slides on this. I don't know how I can easily dig them up, but maybe if you with all the equations correctly written down. Okay, here's the thing written out more carefully. I talked about this tau, the two clocks, tau and sigma clocks. Tau is a function of one. This is one clock. There's another clock. They run at different rates given by this function f. And this is the precise function that ignore the little g between the g and the g tilde. Actually, I had it all right, except that should be minus 1/4.
That's pretty good. That's pretty good.
Why is it the quarter?
That's very much related to this g to the power 4 here in the action.
Oh.
Oh no, let me see. So these are the equations that I wrote earlier. And the fact that there's a g cubed here,
I see.
which means that the energy there's a g to the fourth, is very much connected to that. So if you had the fact that it's g to the fourth has to do with that there are 4 fermions, and I wrote down earlier. If you had 6 3-body operators, then there'd be 6 and it'd be a different power.
Yeah. Yeah, but now I understand why there's 4 fermions, because it's like a pair that's
Yes, it's a pair moving, and so the 1/4 is very much related to the fact it's a pair that moves.
Right.
If it was triplets that were moving, it'd be a different power.
Yes.
But it would still have the same property of time representation
Yes.
invariance, and that gives you all this structure which is closely related to gravity. And,
And so this is a quite idealistic or idealized model. Do you think that, is there any material that can be engineered to, this kind of goes back to the SYK?
Yeah, well, I mean, people, people have trying, like with quantum computers. In terms of materials, there has been a proposal that you could take graphene, sort of a single flake of graphene with a random, with a random edge. And in fact, there is an experiment.
Who is this?
Philip Kim here.
Oh, Philip Kim. We want to interview him next.
Yes.
we can
Just
do
move to the next
just move to
office.
the next office.
So we worked with him on that, and there are
Excellent,
so if you could take a I mean, it's not exactly SYK, but it's some random flake of graphene. You put in a magnetic field and you measure its electrical and thermal properties.
Yes.
So there is one paper, I'm going to co-author with Philip on that.
Oh, so that paper is already published?
Yeah, it's published in Physical Review Letters. Laurel Anderson was a student who did whose effort led to this, actually. And some of the things they observe are quite consistent with the predictions of SYK, but it's still, I mean, the precision is not that great, and
it's still not
not
like
exclusive.
An exact analog.
Yeah.
Which part is the main part that's hardest to obtain in an experimental system to really truly match the SYK?
Well, it's to turn off the single particle hopping. That's the hard part.
The single particle hopping.
Yeah, the 2 fermion term that I mentioned a long time ago.
Because that gives you like that noise that's not pure then.
That brings you back to the Sommerfeld theory.
Right. So you want to have just the pure SYK, no Sommerfeld contribution.
Right. That's right. Yeah.
Yes.
And there's always some.
Yes.
So in the experiment, you have to go to slightly higher temperatures so that you don't see that effect, and so that makes the interpretation a little bit ambiguous. But the trends are consistent. But I mean, my own effort. That's all nice, very nice, but we don't have the tunability in quantum matter to really do this. I think.
Right.
Maybe in using quantum computers, I think people will eventually get there. But my own effort really has been, now the SYK model has taught us a lot. Taught us much more than we expected about black holes. And it's taught us a lot about strongly entangled chaotic dynamics. Can we use that theoretical insight to solve more realistic models? So not really to solve the SYK model. I want to solve a real model.
I see. Yes.
And that's where this Yukawa SYK model comes in, and we have to put it in 2 dimensions. And this is what we've been doing for the last 5 to 10
Right.
years.
So for the Yukawa model, what is modified exactly relative to the SYK?
Well, so there, yes, okay. So here I just told you what fermions that were interacting. So what you do is you take your fermions and put them near a phase transition.
Yes.
Now, as you mentioned at the beginning, each phase transition is described by some scalar field. You have a field phi,
Yeah.
which has some inverted parabolic potential, and when it goes on one side, you have a phase transition.
Yes.
So basically, you add that to SYK. You take fermions with interactions, and you have it interact with a bosonic term, this field phi. That's how you get the Yukawa SYK model. And that, when you put it on a square lattice, you can even put it on a square lattice, you can actually get physics that's, that people working on cuprates would recognize as a model of the cuprates.
Oh, fantastic. So you think that basically by going further this direction from making the SYK model more realistic, and then together with quantum criticality, can we think of it as a compass for room temperature superconductivity? Is this like...
You put it very well. Better than I could. I completely agree with that. That's been our aim, really.
So we can, like, as a message for, let's say, undergraduates who are still looking for a research field.
Right. I mean, exactly the route you mentioned. We take this quantum criticality between these two metals, and we write it in... We use insights from the SYK model or the Yukawa SYK model to start solving its various properties.
This is very cool.
And this is what we've been doing for the last few years. And we've also been comparing them to quantum computer simulations to just keep checking that we're not, going in some totally incorrect direction. And, it's been quite encouraging. And then, so we think we've made a lot of progress here, and now we also know how to get a superconductor out of it. And so we are trying to then understand the onset of this high temperature superconductivity from the strange metal. What BCS described as how you go from a Sommerfeld metal to a superconductor. We are now trying to do that using these SYK methods from the strange metal to the superconductor. That's what we're working on, in fact.
That's really cool.
Paper on that.
Yeah.
So that's where we are today. I think we have learned a lot from SYK, but the time has come to get more realistic, at least as far as this matter is concerned.
How difficult is it every time you add something? Probably the complexity explodes very quickly.
Yeah. I mean, it's not just the complexity, it's also there's so many choices.
Right.
Different models you could do, different approximations you could make.
Is that somewhere where AI could help, that you just give it like a whole...
Are you trying to substitute the physicists with AI?
Like the things that, the things where it's just rote, like trial and error.
Right. Well,
yes.
The theories we're now solving and the methods we're using, in principle, they could have been done 20 years ago. There's really nothing, essential that wasn't known 20 years ago.
It's just that time limiting.
No, but I think it's it's really the issue of there's so many choices.
Right.
And unless you have some guidepost of which direction to go, it's hard to tell what's the right thing to do, because these are very complicated systems, and if you get an answer, there's no real way of checking it even.
But let's say you had 1 million graduate students, like
I don't.
Could you? But maybe if we had an AI scientist and you had 1 million graduate students, each one like just trying one, like absent of a good intuition.
Yeah.
Could one just brute force this by having something that's like high level enough that could just test all of these different...
Are you saying can AI replace me?
Not you, but let's say a first-year graduate student.
I'm skeptical. I think, Anyway, the way SYK kind of gave us a guidepost.
Yes.
This gives you all this interesting behavior, and
Yes.
it gives us which direction to go.
Yeah.
Okay.
Yeah.
And I think that several times in my career, these kind of solvable toy models have helped me get a jump on my competition by having
It's like
insights from some other.
It's like you're the only one having a harmonic oscillator as a mental model to.
Yeah, that's a good way to put it. Yeah. And, and a lot of these insights came from very unexpected places.
Right.
And also by talking to people in other fields, and talking to cold item people, talking to, it wasn't clear that when this work was being, that how would it all connect together. And
yeah, so building
somehow that kind of culture of different fields of science interacting with each other, I mean, people are trying to build agents in AI. Maybe that agents would do that. I don't know.
So instead of maybe AI, I would ask you, how do you make this right decisions, or maybe like we talked about the SYK model, which is big success, but was there any directions you went and it was not a good like about the failures? Or like success to failure ratios? Like how do you?
There's lots of failures. Yeah.
Because everyone, like in science, usually we talk about like the good parts, but no one really talks about like the problems or which doesn't work.
Yeah. Well, we were looking at many different random models at that time. A lot of people were. Why did I pick this particular one? I don't know. But there were certainly lots of failures. Even SYK, when we first solved it, I wasn't clear that this is going to be. I certainly never imagined it anywhere close to the impact that it had. I was almost thinking, well, this is something strange. I not even worth publishing, perhaps. But luckily,
so how did you decide that it's worth publishing?
Well, I was a young professor. I had to justify my existence. So,
so that actually helped.
Yeah.
The publishing pressure.
Parish
Right.
I
said, okay, at least I should publish it. And people asking, what were you up to? Well, this is what I did.
So is it actually?
Did you get criticism in the beginning where people like, oh, this is too simple. Like, why are you looking at this? Did anyone? Or
mostly it was. I'm happy to get criticism. It's when people ignore it, then.
Yes. Any publicity is good publicity.
Right. No, somebody says, okay, that's an idea, but you
can expand.
You can.
Yes.
You have to make. You made a mistake here. Made a mistake. Let's fix that. And
that's great. That's good work. Yes.
Yeah.
Yes.
But if nobody even. That's the worst part. And it took, I think it was 2 years before anybody even mentioned it in any other paper.
Oh wow! That's.
Yeah.
And then it probably exponentially.
And I started working on other things because nobody was paying attention. But I did publish it.
Yes.
And somehow, through some luck, it got published in Physical Review Letters. Initially, it wasn't getting accepted there, but I kept arguing.
So was it just sitting on archive? Or,
there was no archive.
I see. That's why I was.
No. It was. It
was.
Yeah.
Because this is why I found
it. Which year is it?
1992.
So the archive started in. I have one of my proudest accomplishments is I have the very first paper on the condensed matter archive.
Oh really?
Oh wow!
So that's 9204001. That's also with my same students. So that's April of 92. This paper is December of 92. So
you're the pioneer of the archive.
It had just started.
Yeah.
And many people were not submitting to the archive.
Of course.
How did you hear about the archive system?
Well, it started in string theory before.
Mm-hmm.
It started in 1 or 2 years before. And then I just somehow heard initially the condensed matter archive was started in Trieste. That's where they started it over there.
ICDP?
At CISA, actually.
CISA, I see.
Yeah. And somehow I heard somebody said, CISA is starting something for condensed matter. Oh, great. I have this paper I've just finished. Let me put it there.
Amazing.
In those days, I think the first 2 days there was only one paper. Why? So
You at the right time, at the right place to hand out your paper.
yeah, but and many people didn't even know, it was a while before the senior people in the field started sending their papers
Yes.
to the archive. Not right away. It took a year or two
Yes.
before everyone started going in that direction. But initially it was viewed as something strange. It's so useful, and I can't imagine life without it.
Oh, absolutely. Yes.
The fastest dissemination
Yes.
of the knowledge.
Yeah. So it was, so you were talking about something else. Yes. So you were asking about, get a million students or AI.
How about unlimited resources? Like it could be students, could be, I don't know, access to quantum computers, to AI systems, or
Let's say you had infinite
Fun.
money or infinite students. What would you do? What would you ask them to do? Or what would you use the infinite amount of money to do?
So, okay, my personal experience is science moves at a certain pace, and things, ideas have to be put out there, absorbed and discussed, and connections to different observations have to come in. And
So you can't just
I
parallelize
don't
it. And,
think you
yes,
can.
Yes.
I think that's really
There's a
intrinsic
rate
part of
limit.
doing science. Yeah.
It's a rate limited process.
It's not, it's a very complicated natural world we're dealing with. And, of course, there are a lot of brilliant people who, but, even someone as brilliant as Ed Witten could not have invented string theory all by himself.
Yes.
It is
yes.
a lot of
Back and forth.
ideas
Yeah.
come from random directions which nobody expected, and then,
random walk. And then we
and
publish something.
I don't see as yet how AI is built to really
Right.
do that.
Right.
I mean, there's certainly huge progress in the way AI is set up, and the question is how do we use that progress to do better science? And
Maybe it could inspire, as a dialogue. Like that's
so-
why I would sometimes use to instead of in addition talking to someone, you can talk to a lot of course with person. It's much better.
But I think the where it has it so far, it's more of it's given us a remarkable tool to optimize functions in high dimension spaces, and that and that's a problem that kind of problem is present in many different fields of science. So you have to take those tools to do the optimization. You can use AI. You start playing chess, then it's all the folding problem. These are very specific optimization.
Yes.
What's the best move to make here,
Yes.
and so on. What is the best term to add in this model to get this behavior? Maybe it will start answering these questions, and maybe that will eventually have an impact on experiments. We will see.
On a slightly different note,
Yeah.
you've probably followed all that media buzz about LK99, like
Oh, that was one
every
guy.
few years there is like a room temperature superconductor. What do you think of this cycle happening? Like, why is it happening? Why do we have every 2 years someone who claims they have a room temperature superconductor and
Well, it's unfortunate that, after the LK99, I think they saw an effect, and which has not been reproduced. There have been many other reports, and
Yes.
that's fine. I mean, that's part of doing science. You have to check it, and people get excited. But there have been a few instances where there seems to have been, actual misrepresentation, and that's terrible.
Yes. Yes.
So, I mean, from my point of view is, when I used to tell people I'm working superconductivity, that you get a blank look. But now suddenly everyone knew a little bit about superconductivity.
You have to be informed.
Yeah, and the public is learning about superconductivity, maybe not in the best way. But,
Because all of a sudden people were streaming themselves on Twitch as they were trying to synthesize LK99, and so it's become an interesting.
right. Yeah. But and it is very important that the scientific method be followed, that people reproduce it in a lab under specified conditions, and it be evaluated by referees, and there's no shortcut around that. And so science publication has to learn how to deal with social media. Right? That's the difference now.
When people come up with these
anybody
claims,
can put something on Twitter, and then the whole world knows about it. That wasn't possible before. And so now that's affecting science, and we have to learn how to deal with it. But ultimately, the press, the more responsible press, has to also play a role in not hyping things until they have been properly evaluated.
But it seems that in this particular case, the corrective mechanism actually worked, because people did collectively then arrive at the conclusion that this was not room temperature superconductivity.
Right. I mean, so it led the effect. Well, there's all the superconductor, but not really. But that's a bit unfortunate, because there are a lot of good superconductors, and under high pressure, there are these hydrides which really are now being verified to be not room temperature, but under very high pressure, be rather high temperature superconductors. Well, when the cuprates first came out in '87, that was also on the front page of the New York Times, and that turned out to be correct. But people have forgotten that, And but fact remains, they're still the best superconductors. They're the materials being used in the fusion machines, not anything else. And it relates to what we said earlier, that liquid nitrogen is not so hard to make. So that's not the real problem. Getting it to room temperature may not really make things that much better if the material is not better behaved.
It
has to, you have to make wires, and you have to be able to carry a lot of current. It has to be able to withstand damage from radiation. These are the important issues, and not so much the temperature, I think.
But once we could get it to room temperature without all of those issues, we could literally have it in any kind of electronic device.
If it's scalable, if you can produce it, then
imagine your iPhone just running at 30% low. I don't think it would like that.
It doesn't violate conservation of energy. It gives you efficient way to transfer power from one point to the other. You still need batteries.
You still need batteries. They will last longer.
High voltage.
You have fewer losses. Along the way. Actually,
I was thinking, since we touched the base on the textbooks, so what are your views on what are the best ways to maybe train and bring up the theoretical physicists? Like, let's say, I don't know, that was a while ago, or maybe still like Landau school, where there was a strict like theoretical minimum, like you have to pass through all of the volumes, learn how to.
I mean, you could
solve problems. What's your
teaching philosophy or didactic philosophy?
How to train the.
There's certainly certain basics of quantum field theory and specific mechanics. I think essential for everybody. I think what has changed recently is there's much more emphasis on discrete quantum theory, qubits and gates and networks, and that is a very new way of thinking, which is also very useful in many contexts. And so I think that some of the older books, maybe including mine to some extent, need to update it with that new point of view. But there's no, in my view, there's no substitute for taking some fraction of the Landau minimum. Everyone has to really.
Is there like a set of I don't know, theorems, or like you ask your students who would like to join your group, like is there like a minimum of skills they need to
Yeah, well, I mean, you need to know a little bit about second quantization, these operators I wrote down, how Schrödinger's equation in different situations, and a little bit of many-body theory. I guess nowadays even topology is playing a bit of a role.
Right.
Yeah, which is totally missing from Landau's.
So like differential geometry as well.
Yeah, I don't know if you really
That's on the cosmology
That's
side.
more the GR people.
Yeah.
Yeah. Well, I think just a good course in quantum mechanics and a good course in system mechanics and maybe a little bit of quantum field theory, which is the content of a typical first year course at any graduate school in physics, anywhere in the world, really.
What do you teach at Harvard, or what was the typical
It varies,
class? Yeah.
but I end up teaching quantum many-body theory a lot and solid-state physics. So, theory of metals. I start with Sommerfeld.
Yes.
And then I go up to PCS,
Yes.
1957, and then try to jump to more modern topics.
All right.
Yeah.
I think
Okay.
Thank you. Thank you so
Thank you.
much. Like a
Thank
day
you.
before Thanksgiving. Yes.
I didn't think you'd want to talk for 3 hours, but I was certainly very happy that you did.
Oh, we're very happy that
Okay.
that you took the
Yeah, that was
time. Like
amazing.
this was really good. This was,
Okay.
I learned so much.
All right.
Likewise.
Thank you. Wow. Okay.
Thank you.
Subir.
All right.